Today we're going to talk about using something called the lens equation to predict the location of an image if we know the focal length and the distance of the light source or the object away from a convex lens. The lens equation is 1 over dO plus 1 over dI equals 1 over F. dO is the distance to the object from the lens. dI is the distance to the image from the lens. F is the focal length of the lens. So we're going to start with the first problem on page 11, which is part of something called the Lens Equation Lab. And the first thing I'm going to do is draw a little picture of of what we're talking about here, so you have an idea what it looks like, and then we'll go from there to talk about solving the lens equation. So first of all, I'm going to make a picture of this. Today it says we will calculate the image distance when a light source, which would be an object, is placed in front of a lens with a known focal length. And we will check out our solutions with a light source, lens, screen, and an optics bench. So we're going to do the calculations first, and we're going to save the checking out the solutions for later. Okay, so first off, the light source is 0.4 meters away from a convex lens. So this is a convex lens, and the light source, dO then, is equal to 0.4 meters. Now, this is positive. This is a positive number. Okay? And the lens has a focal length, F, equal to 0.1 meters. And this is also positive. Okay? Okay. The lens equation is 1 over dO plus 1 over dI equals 1 over the focal length. So you can see over here, the focal length, F, is equal to 0.1, and the object distance is equal to 0.4. Okay, now we're going to solve for dI. Okay? Okay, so let's draw a picture of this. So we have a convex lens. And that's the principal axis. This is the normal axis. And we have a focal length of 0.1 meters. That's F. 0.1 meters. That's F. C would be 2 times the focal length, so it'd be 0.2 meters. And the object, the light source, would be located way out here. And the dO on that, from here back to the lens, the dO would be 0.4 meters. So in this case, the dO is greater than C, or 2F. Okay? So the case we're looking at here is a case which, if you look at the table that we have, would be what we would call a SIR case. The image should be smaller, inverted, and real. Well, let's see if that's true. So where would the image be? Well, first of all, I would draw a line like this, and then I would go down to the focal point, and I would draw a second line through the vertex. These two lines would intersect here, and the image would be located right here. So the image would be smaller, it would be inverted, and it would be real. So this is where the image would be located. Here's where the object is. Okay, so let's kind of confirm this with some numbers. So if we substitute this in to this equation and do it mathematically, what we would get would be 1 over 0.4 plus 1 over di equals 1 over 0.1. If I do the math on that, that would give me 1 over di equals 10 minus 2.5. Okay? Or 1 over di would be equal to 7.5. di then would be equal to 0.133 meters. And it would be positive. Okay, so di we would calculate at 0.133 meters. And that would be a positive number. And if you look at the convex case where the object is beyond C, you'll see that the image is smaller, inverted, and up and real, and the di is positive. So this image would be smaller, inverted, and real, and would be located as shown down here on this graph. Okay, so what I'd like you to do then is take this kind of approach and go down through the rest of the table. Okay, and fill those in. And what I'd like you to assume for the object distance for the second to the bottom one is 0.15 for a DO. And for the bottom one, I'd like you to assume a focal length, F, equal to 0.2 meters, and an object distance, DO, equal to 0.3 meters. Okay? And basically do this kind of work that we just did, I just showed you, on all these other cases all the way down the page.